Hello everyone and welcome to the first lesson here in our second unit. This second unit is really dominated by one big question. We're going to kind of dig into that today. Please make sure you follow along, take notes in your Unit 2 student packet. You can find that posted on Google Classroom or you picked up a hard copy maybe. And take notes on there, and if I ask you to pause the video and try some things, please do. All right? So the big question that we're really going to be wrestling with this unit is the following. Let's make this a little smaller. How try this again. How can we talk about the way a function changes at a point? How can we talk about the way a function changes at a point? Now, this might sound somewhat familiar because when we were just starting off this year, I kind of teased this idea of the average rate of change. If we want to find the slope of a line between 2 points, we can use the average rate of change. But then we can sort of develop a process to find the slope of a line that passes through a single point on a curve, an instantaneous rate of change. And that is what we're going to be exploring a little more today. All right. Let's kind of get into it. And I like this example as our first time into this idea. Let's consider the graph of the two race cars over here. We got a red car, we got a black car. The driver's distance is along the vertical axis, and the time being measured is along the horizontal axis. So it looks like the red car started a little farther down the track. Okay. How can we calculate the average velocity of each car over the entire race? Well, the entire race, if we look there, the entire race for each of the cars is a little different. For our red car, actually this doesn't make sense if I do this in red probably. For our red car, the points here and here represent the beginning and the end of the race. But the y-axis measures distance. If I want to know velocity I know is measured in things like meters per second. So that sounds like a slope. So if I take the slope between those points there, if I take the slope starting from here until here, if I find that slope, I should be able to find the average velocity of this red car. And I can do that. The average velocity might be something like this. This ending point over here we need to know is 10, right? 10, 160. And our starting point over here was 0, 30. Now if I want to find that slope, it would be 160 minus 30. And the units of 160 and 30 are meters over 10 minus 0 seconds. Or that would be 130 over 10 meters per second. We don't need to simplify stuff this year. We're just going to leave things unsimplified as much as possible, actually. Now we can do something similar for our black car. If I want to know the black car's average velocity, on average, how fast is this car going? That would be a slope also, a rate of change. Slopes are rates of change. All right, so I could start here and find the slope across that entire interval for our black car. So let's figure out those starting and ending points. At the beginning here, we have 1, 0, and at the end of that car's journey, 12, 160. Ooh, my 160 got a little squished there, but there we go. All right. So for the black car, its slope would be 160 minus 0 meters over 12 minus 1 second. And notice, just finding the slope here, the units work out and we end up with meters per second, which is a velocity. So that's 160 over 11 meters per second. So the average velocity over here was 13 meters per second, and over here was 160 divided by 11 meters per second, which if we want to put a more concrete number on that, is 14 and a half-ish. So actually our black car on average was traveling faster. So that's how we calculate average velocities. We want to know the average rate of change of something. We found the rate of change of distance. We can simply do a slope between endpoints. This is the same thing that we found. This average velocity is really what we call an average rate of change. That's a phrase we'll hear a lot this year. Average rate of change. I'll sometimes abbreviate that AROC, A-R-O-C. And the average rate of change formula is just our slope formula. F of B minus F of A over B minus A finds us the average rate of change on the interval A to B. All right? In other words, we're finding the rate of change of distance over time. So what would the average velocity, so we're given distance, velocity would be the rate of change of distance. How is distance changing? The average velocity for each car from 2 to 9. All right, well, we would need the points. Let's see, for the red car, on the interval, we read this interval notation as from 2 to 9 inclusive. For our black car, our point is right there. That'd be 2, 30. And then 9, our black car would be the point 9, would that be 115? And for our red car, our point would be 2, 75. And our ending point, 9 over here, would be the point 9, 140. My eyes do not deceive me. All right. And we can find those average rates of change. Again, we won't simplify, but for the red car, that'd be 140 minus 75 meters over 9 minus 2 seconds, whatever that comes out to be. And for our black car, it'd be 115 minus 30 meters per 9 minus 2 seconds. And again, we don't need to simplify. If you're the kind of person you're really bothered by that, you can. But the point of not simplifying is that we don't accidentally make numerical errors. But if you want to, you could say this is 85 sevenths meters per second. And that would be equivalent, right? All right. Cool. So we've seen now a couple examples of how to find the average rate of change, right? Now, what if I wanted a general equation for the average rate of change of the black car from 4 to some unknown time? So looking back at this black car, what if I wanted kind of a general statement for the average rate of change from 4 to some unknown time t? Well, that means I would have the point f of 4, which I would know. But then I would also be comparing it to f of t, some unknown in time. And if I want to, I could come up with an equation that maybe says this for our average rate of change. F of t, I could call that like my f of b, minus f of 4 over 4 minus t, where f is the distance of the black car. So this might translate into something like f of t minus f of 4. At 4, our black car looks like it's at 75 meters over 4 minus, or I made a mistake there. Let's back up for a second. If I did f of t minus f of 4, that means my denominator needs to be t minus 4. Sorry about that. Which means over here, I would also have t minus 4. Now this is kind of just like a generalization of our average rate of change. Up here I was using concrete numbers, ending point minus starting point over ending point minus starting point. But if we don't know the ending time, I can just kind of leave it general like this. All right? We'll kind of see something similar to this pop up, which is why I want to bring it up now. 3. When are the cars traveling the fastest, and how do we know? Pause and think about that for a second. Think to yourself, based off the graph, when are the cars traveling the slowest? And how do you know? When are the cars traveling the slowest? And how do you know? Think. All right, well, if we said that the velocity, the average velocity is measured by a slope, slowest, if we're comparing or thinking about velocity as slope, slowest would make it sound like our slope is actually small or pretty flat. And that would be correct. When are the cars traveling the slowest? When the slope of the distance graphs is smallest. And by smallest, we mean close to 0 or closest to 0. All right? And that's because slope measures the rate of change of distance, which is velocity. So I don't know, we can imagine a situation like in here, for example, and there's where it looks like the slope would be the smallest. If I tried to just draw like a slope that goes right along there, it might be something like that. It's a pretty shallow slope. So at about 7 seconds or so for the black car, 7 seconds for black. And then for our red car, I don't know, what does it look like? Where does it look like our slope would be the shallowest here? Maybe somewhere in that area there. So maybe about 6 seconds for black. No, I mean, not black, for red. Yeah, we're looking at when the slope of the distance graphs is the smallest. That would be a moment when our cars are traveling the slowest. So that, if we're talking about a specific moment and we want a specific speed at a specific time, that is what we call the instantaneous rate of change. So can we calculate the instantaneous speed of the cars at t equals 4 using the graph? The answer here is no. Just using the graph, we can't just measure what is the speed of the car at t equals 4. No, we can't use just the graph. We can't use the graph to determine an instantaneous speed. But those little lines that I drew in here, those little lines we drew in here, have a name. They have a special name. If I go back up here and I were to draw in another one of those little lines that represent the slope at a specific point have a name. Those lines that kind of just skim the surface of the graph are what we call tangent lines. Now, we can't just use a graph to determine the slope of a tangent line, but the tangent line, a line that just skims the surface of the graph, the slope of the tangent line, is the same thing as what we call the instantaneous rate of change. That's ultimately what we're interested in here in calculus. What is the instantaneous rate of change? What is the slope of that tangent line that just skims the surface of a graph? Earlier we talked about the average rate of change, which is across an interval. Average rate of change. And those lines I drew initially that kind of connect 2 points are called secant lines. The slope of a secant line gives us the average rate of change. That's when we have 2 points and we connect them. That's a secant line if we connect 2 points on a graph. A tangent line just skims the graph at one place. We call that the instantaneous rate of change if we can find that slope. That's going to be our focus this unit. All right. Now we can do this also just from tables and things too. We can find average rates of change and work on approximating instantaneous rates of change from tables. So I'm going to go ahead and give this a shot. Suppose we only have a few values of some function that we know is continuous, and here's a table of values. Go ahead and find the average rate of change of fx over the interval 2 to 11. And then do b. What is the slope of the secant line through points for f of 3 and f of 8? Go ahead and do that. All right, let's take a look. If we want the average rate of change on the interval 2 to 11, we need to first identify those values. There we go, and there we go. And we need to do f of b, which is 4, minus f of a, which is 7, over b minus a. So we end up with -3/9 or -1/3. There we go. There would be the average rate of change over that interval. A slope of a secant line is the same thing as the average rate of change. This is really the same thing. This time we want f of 3 and f of 8. So f of 3 is here. F of 8 is here. So f of 8 minus f of 3 over 8 minus 3. It's also really good to write out the function notation of this first, just so that your reader knows you know what you're talking about. So this would be 3 minus 10, f of 8 minus f of 3 over 8 minus 3 will give us -7/5. All right. Now here's a new word, approximate the derivative. Now we've already seen this term slope of a tangent line. The slope of a tangent line, which we said is the same thing as the instantaneous, I'm going to abbreviate that, instantaneous rate of change, is also known in calculus by the word derivative. And that's what we'll use most often. When I say derivative, I mean the slope of the tangent line, the instantaneous rate of change. And again, a tangent line, if we have some curve, is a line that just skims the surface there. That's what we call the derivative. Now, we can't, as we said, just determine that from these points. We don't actually have a way to. And if we just think about this a step farther, wait a minute, if we want it at x equals 7, we're going to run into some issues because 7, x equals 7, isn't even on this graph. X equals 7 would be right here. But if we just need to approximate the derivative, what would the slope at 7 be? We can use the surrounding points. And we could say this, that the derivative at 7 is going to be approximately f of 8 minus f of 6 over 8 minus 6. That'll get pretty close to figuring us out the slope at 7. We find the slope between two nearby points. All right? So f of 8 is 3, f of 6 is 4 over 8 minus 6 will give us -1 over 2. There we go. Now, what would give us a better approximation of the slope of that tangent line? If we somehow wanted to get a better approximation of the slope right at 7, not using two nearby points like the 2 points 6 and 8 at x equals 6 and x equals 8, what would give us a better approximation of the slope of the tangent line at x equals 7? Think about that for a second. What would give us a better approximation of the slope of the tangent line at x equals 7? Well, if you think for a second, you might go, well, using x equals 6 and x equals 8, those points are kind of far away from 7. Couldn't we get points closer? And the answer is yes. If we had points closer to x equals 7, our slope approximation for the slope at x equals 7 would be better. So basically, if we think about sliding these 2 points in, if we could cinch those points in, 6 and 8, closer to 7, we'd have a better approximation of what's going on at x equals 7. All right, we can do this also from functions, okay? Go ahead and I want you to see if you can answer questions A and B here based off of that function. Go ahead and try that. All right, here we go. Average rate of change. That means we need g of 2. Since we're on the interval 0 to 2, g of 2 minus g of 0 over 2 minus 0. G of 2, when I plug in, that'll give me 8 minus 6 plus 1. Which will give me 3. 3 minus, when I plug in 0 in here, I get 1. 3 minus 1 over 2. So 1 if I want to simplify. There's the average rate of change on the interval 0 to 2. Got my y values, subtracted them, divided by the difference in the x values. Slope of the secant line. That's the same thing as the average rate of change we've been saying. So this time we want to find the average rate of change on the interval -1 to 1. So I would need g of 1 minus g of -1 over 1 minus -1. If I go back up there and I say, okay, well, I need to know what g of 1 is. G of 1, when I plug in 1 up here, is going to be 2 minus 3 plus 1 will give me 0 minus g of negative 1. So if I plug in negative 1, I'll have 2 plus 3 plus 1, which will give me 6. All right, all over 2, which will give me negative 3 in the end. Okay. So this is the average rate of change. Now, what if we wanted to write two limits that could be used to determine the derivative g of t at t equals 1? So last time we kind of had to approximate. We had to get nearby points. Now let's imagine a situation like this. Let's imagine we know we want to find the derivative or the slope of the tangent line, the instantaneous rate of change, the slope of the tangent line at t equals 1. Well, in my slope formula, I would have something like g of 1. Actually, let's do it this way. I know that g of 1 is going to be one of my points of interest, right? So I could write it out like this. G of t, the point I don't know, minus, actually, pull it together, Markwalter. Let's call our nearby point that we don't know, that we're going to use something like g of a. So let's say we're going to do g of a minus g of 1 over a minus 1. That would work, right? If we wanted to find or try to determine the derivative, the slope of the tangent line at 1, we would need some nearby point. But a is right now just a placeholder. If we want a to be really nearby 1 to be able to find a slope, we would need to say something like the limit as a approaches 1. Basically what this is saying is, hey, let's take an x value really, 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 really close to 1 and find the slope between that really, really close value and 1. In other words, on a graph, we're taking two really, 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 really close nearby points and find the slope between them. And if those points are infinitely close together, we're finding the slope of the tangent line. We're basically slamming these 2 points together until they're infinitely close and behave like a single point. All right? So that could work. Now there's another way we could do this using limits. Since these 2 points are like really close together, also sometimes, in case you want to know, sometimes this limit is written out like this instead, g of 1 minus g of a over 1 minus a. Now, another option for how we can do this is, since the 2 points are going to be really, really close by each other, let's say we have g of 1, the point we're interested in, and we want to find the difference between 1 plus some small little bit, all right? And so our second point is just going to be 1 plus some little tiny amount over 1 minus whatever that 1 plus the tiny amount is. Think of this little x value thing in here as we've just moved over a little bit. We've just moved over a tiny little bit on our graph. Now, if we want to tell mathematically, hey, we're just moving over a tiny little bit, then let's say that the limit is h approaches 0. H is how far we move over to get to that second point, and let's just say we move over an infinitely tiny little bit to get to that second point. Okay? We're going to talk about this stuff a little more later. We're just kind of teasing these ideas right now. This limit would also find for us the slope of the tangent line. We're starting at some t value where we're interested in finding the slope, and then we're comparing it to a point that's really close by. We know it's really close by because we're doing 1 plus h, and h, how far over we're moving, is going to 0. You don't need to really know these yet. I just want to kind of seed them in your mind. Okay. Next up, I would like you to do this. I want you to take a look at this problem, pause the video, and give questions 1 through 5 a shot, please. All right, let's quickly run through this. Which runner has a faster average speed for the first 9 seconds? For the first 9 seconds, looking at runner A and runner B, if I do A first, I would have 120 minus 0 over 9 minus 0. And runner B, I would have 120 minus 0 over 9 minus 0. We can use our graph there to find this point, or the table. Turns out they have the same average speed. over that first interval. Which runner has the faster average speed from 9 to 20 seconds? Well, runner A, 9 to 20 seconds. Runner A would be 168 minus 120 over 20 minus 9, which if we do simplify that, since we're asked to actually determine this, we might need to simplify to be able to get a good number. 168 minus 120 divided by 11 gives us about 364. In calculus, we're always going to go to 3 decimal places. That's a set thing here in this course, right? And B, from 9 to 20 seconds, that'd be 213 minus 120 over 20 minus 9, which is going to give us something faster. We can already tell, right? 213 minus 120 divided by 11 is going to give us 8.455. All right. So runner B was faster. Which runner has a faster average speed from 20 to 31 seconds? All right. From 20 to 31 seconds, we can do something similar. We would have 287 minus 168 over 31 minus 20. B here. 287 minus 213 over 31 minus 20. And just comparing those, if you kind of think about what's going on here, the faster runner over that interval is going to be our runner A. And you can calculate those down if you want to. Which runner has the faster average speed from 9 to 31? From 9 to 31. If you do that calculation, you actually end up with the same value. Both runner A and runner B, in this case, have 287 minus 120 over 31 minus 9. Notice they start and end both at the same values there. So they are the same speed. And which runner wins the race? Now we got to be careful. It is a 400-meter race, so this doesn't help us out. We have to look at our graph. The runner A wins the race. A, because A completes 400 meters faster than B. And that we have to get from the graph up here. All right, I want to do an example here for you before we close out. For each problem, I want you to find the average rate of change of the function over the given interval. All right, so we're given some function, we're given some interval. We want to find the average rate of change over the given interval, and then write 2 limits that could be used to evaluate the derivative of the function at x equals 1. All right, and I'm going to show you how I want you to write those, so you just practice writing them. All right. So here we'd have for average rate of change f of 1 minus f of 0 over 1 minus 0. F of 1, when I plug in, is going to give me negative 2 plus 1 minus 2. All right, so that's going to give me negative 3. Minus, when I plug in f of 0, I'm going to get negative 2. So I get negative 3 minus negative 2 over 1. So that comes out to be negative 1 over 1, or negative 1. Okay. Now that's the average rate of change. What if we wanted to evaluate the derivative of the function at x equals 1? All right. This I do want to solidify down a little bit more, and then you're going to practice this. All right. So one method here that I want us to use is this. Okay. Based off that first limit thing I wrote above, one of the possible ways we can write out a limit definition of a derivative is to say this. Let's say we're going to take f of x and making it closer and closer to f of 1 over x minus 1. We leave this 1 here because that's where we're trying to take the derivative. But we want to make that other point get closer and closer to 1. That place we're interested in taking the derivative. Remember, we're thinking about if we want a good approximation of the derivative, that slope of the tangent line, we got to get our 2 points really, really close together near our point of interest. So this is one of the limits that will find for us that derivative. The other limit looks like this. We could have the point f of, ooh, that got a little funky looking, f of 1. And we could say our other point is f of 1 plus, we've moved over a little bit. I know my last one I switched those around. The order doesn't actually matter as long as we keep it consistent from numerator to denominator, but these two are the standard ways we write this now. So down here we would have 1 plus h, that's our first x value, minus 1. But 1 plus h minus 1, that x value, the ones that cancel out and leave us with just h. So these two are standard ways of writing out the derivative at x equals 1. Now, if we want to, we could then go back in and actually plug in our values here that we know from our functions. So I could come in here, for example, for this one and say that this is the limit as x approaches 1 of f of x, which is up here. That'd be negative 2x squared plus x minus 2 minus f of 1. And what is f of 1? Oh, f of 1 was right there. We already found it. F of 1 was negative 3, so minus negative 3. All over x minus 1. That would be our limit definition of a derivative if we actually wrote out the function and substituted in our things. We could do something similar up here. For today, what I want you to do to close out is I want you to go ahead and find the average rate of change across the interval for each of numbers 2, 3, and 4. Okay? 2, 3, and 4. And then I want you to write out exactly what I did here in black, the limit definition of a derivative. Just get used to writing it. Even if you don't understand what it means yet, just get used to writing it. And then for this first limit definition you write out, go ahead and substitute in the actual f of x and known values into it and rewrite the limit without function notation. You do not need to do that for the second one yet. Okay? So at the end of this video, you're going to do 2, 3, 4. You're going to find the average rate of change on the interval and write out your two limit definitions like I did in black, and then write out like the one in red by substituting in the known function values for the first limit definition. All right? Go ahead and do that, and don't forget you can take care of the optional homework too if you want more practice. If you're feeling confused about the derivatives here, we're going to spend a lot of time with them. That is all right. All right, take care everyone. Have a good weekend.